Alright, good afternoon everyone. We are the Sprinkler Activation Detection Project. We work for FM Global, like you said. Our advisor is Professor Arsoon. I'm James Patterson, Steve Rada, Kyle Frisco, and Peter Key. So some of you are probably wondering, who is FM Global? So FM Global is a Fortune 1000 property insurance company. So what they deal with is, most insurance companies use statistics to back their insurance, but they use research, which is very different. So they're a very large company. For this specific project, we're dealing with fire protection. So the picture on the right is from one of their labs at their research campus in Rhode Island. What they do here is they'll set up an array of commodities to burn, run a burn test, then the sprinklers will activate based on how that fire burns. Then they can know, all right, the sprinkler system works or it doesn't work, and then that helps back their insurance. So what FM tasked us to do is come up with a way to show when a specific sprinkler activates with non-intrusive method. So the schematic on the right is what would be typically in one of their control rooms at their labs. The blue lines are pipes and the black dots are sprinklers. Once one sprinkler activates, we want to be able to have it show up as a red dot, just like that did, so we know, okay, that specific sprinkler is active and the water is dumping at that section of the fire. Quick note, this is only going to be used for research purposes in their labs at their facilities, so it's not going to be implemented anywhere else. So the current method that they use to detect this is they connect a wire to the sprinkler, the pipe is grounded, and a 5-volt charge is added to that. So then there is a circuit, a connected circuit with 5 volts. Once the sprinkler activates, that wire that's connected to the plug of the sprinkler leaves, that circuit's broken, and then that drop in voltage is how they see activation. So the issue with this is that it's intrusive to the sprinkler because they're attaching the wire to it. Now if they have, say, an issue with the sprinkler, it doesn't activate, or any kind of issue, now the sprinkler company can come back on them and say, okay, the reason why it didn't work was because you tampered with it. So this can get expensive because they'll have to redo tests. It's also time consuming, which time is money. So the solution that we came up with is to take an LED on the top side of our pipe, shine it down through to the back side of the sprinkler. Also, have a sensor on the exterior that collects that light. So once the sprinkler activates, the light shines through that sensor, which the sensor that we chose is a photodiode, which just converts light to voltage. The LED we're going to use is a red LED for a large wavelength, and it's also going to be pulsed for filtering reasons. Now Kyle is going to talk about our testing unit.
So our first step into solving our suggested solution was designing our testing unit. We used SolidWorks to design our 5-foot steel pipe jig that can withstand up to 150 psi of pressure. This pipe would see 3 different variations of testing: pressurized air, pressurized water, and initially the pipe would be dry, and then upon sprinkler activation, the water would be flushed into the pipe. As you can see, our pipe has been assembled with Victaulic fittings. The 2 Victaulic fittings that you see in the middle have threads on both the top and bottom. This gives us the ability to use 2 sprinklers at once for a test. We need to use 2 sprinklers at once for a test so that we can ensure that there will be no false activation for a neighboring sprinkler. Once we had our pipe delivered from FM, we then moved on to our plug design. As you can see, we had many iterations for our plug design. We were able to use a 3D printer on campus to continuously test and redesign our plug. Working in tandem with our client, we were able to make sure that we met all their preferences. So after we had our plug and our pipe, we then moved on to our brackets. As you can see, we had 2 iterations of our concepts. On the left, you can see the ring bracket. This bracket had the ability to collect the most light, but unfortunately, it was too close to the sprinkler, which was in the way of the spray pattern. This was a big concern for our client. So we stepped away from the ring bracket, and then as you can see on the right, we went with the clamp-on bracket, which was further away from the sprinkler. But in doing so, we actually ran into more complications with alignment issues. So with the alignment issues, we concluded that the setup time had actually increased, and FM is trying to decrease that setup time. So we tried to take both pros of our previous designs, and now you can see we have our final design. It's simply clamps onto the pipe, and it has an adjustable holster that will hold our photodiode sensor. I know you're probably wondering that bracket's still really close to the sprinkler, but we had tested it multiple times in lab and concluded that it was not in the spray pattern. And for our adjustable holster, this makes our design universal, essentially, because FM uses various size sprinklers during testing. So if they're switching from a smaller sprinkler to a bigger sprinkler, all it takes is a little loosening and adjusting to that sprinkler. This is also huge because it's going to cut down costs for the technicians to adjust to those sprinklers. And now Stephen is going to talk about our testing procedure.
So testing was a big part of this project, reviewing those results and then redesign, coming back to the testing procedure. So a typical test was setting up our computer and sensor, moving to getting the right angle to get the most collection. We did this by putting an already activated sprinkler into the slot, shining the light through, and then making sure that we're getting data collection in our LabVIEW program. From there we move on to a dry test, which consists of using a non-activated sprinkler but no water. We activate the sprinkler and then look for that jump in the LabVIEW, which I'll show later, just to get a timely validation to show that it was activated. From there we pressurize our pipe jig with water up to 60 psi, and then activate it, letting the water come out, and essentially evaluating the same values that we did for the dry test. So here we have our electrical setup. On the left here we have an amplifier which takes the voltage reading that's collected by the photodiode and just increases it so that it can be detected by our DAC card that you can see over here. The DAC card then takes that reading and transmits it to our LabVIEW program for visualization. Down below here is our Arduino, which is what we use to pulse our LED at a given frequency to prevent any interference from other lights. And over here we have a voltage limiter, just to prevent any chance of blowing out our LED during extended testing. It was just a safety precaution. So here's a view of what we look at on the computer screen, our LabVIEW program. This top graph right here is the voltage amplitude collected by the photodiode. It takes that, and when you see a spike here, that's what we're looking for from the light coming through the sprinkler head and detection from the photodiode. Just below that is a frequency reading. What we have our detection set to is to respond to a frequency of 50 Hertz plus or minus 10%, and that value, when it's reached, gives us a step function from 0 to 1. That's what we're looking for from a detection, because it's the light coming from the LED, and in every activation, that's the main focus for it. Here we have a video of a wet test. On the left, you're going to see a sprinkler activate. Water's going to come through, and the light will shine. And on the right, when that happens, you're going to see that spike in voltage, and just below that spike up in frequency. And as you can see, we have that step function that indicates an activation. Here we have a comparison between the wire method and our LED method. You can see on the multimeter that the voltage drops, and that corresponds to a spike in the step function just to the right. This just confirms that both methods are working, the sprinkler activated, and everything went well with the test. So now Pete's going to talk about the design comparisons.
So, as you can see from the video, both these methods will show a sprinkler activation. To compare, we decided to do a simple pros and cons list. On the left here, we have our wire method. Some of the pros are it's simple, inexpensive, and it's responsive. More importantly are its cons. It's intrusive. As James was saying earlier, FM Global doesn't want the sprinkler company to come to them and say that the reason why it didn't work is because they tampered with it. And finally, it's going to be very time-consuming to set up. They can run multiple tests. Each test can have 80 sprinklers, and the technicians are going to have to wire each one of these sprinklers. Now, to fix that, we decided to have a non-intrusive method that we kept all our parts away from the sprinkler. It's a one-time setup, and it's just as responsive as the wire method. On the other hand, we are still going to have to adjust the optic, but the time that this takes isn't going to be nearly as long as it would be to set up this wire method. And lastly, we're going to have to heat-proof our entire project. For heat protection, it is very important because the ambient air can reach up to a maximum temperature of 2,500 degrees Fahrenheit. And to do so, we decided to make a cap. This cap's been made out of stainless steel, which can resist up to 2,000 degrees Fahrenheit. And as you can see in the picture on the left, it has a pocket for insulation that we're going to put in there. This high temp insulation can also resist up to 2,000 degrees Fahrenheit. Now on the right here, we have our high temp casing. And this casing can resist up to 2,600 degrees Fahrenheit. And we're going to put this around our fiber optic and wires coming out of the LED plug. So for our final product, we're going to keep moving forward with our bracket design. We're going to make it out of stainless steel so it can also resist the heat. Now right here we have our LED setup and our plug. This plug is being made out of a 1-inch NPT stainless steel plug that we're going to mill out the middle and put threads on the inside and outside and epoxy a glass to it to serve as a window for the LED. On the top right here we have our heatsink that's made out of aluminum, and we're going to put threads on the outside so it can thread into the plug. In the middle, we see our entire setup together. We have the LED, the heatsink, and in the middle, we're going to have our wires running through. And the most important thing up front, we have our focusing optic. This optic is very important for our project because it takes all the potential light that would be dispersed throughout the pipe and focus it through the sprinkler, allowing us to collect the most light out of that. This is our timeline budget. Throughout the entire year, we were able to overcome any challenges as a team, stay $700 on our budget, finish everything on time, and present what you see here today. For team responsibilities, we have Steven, who was our 3D design expert. We have me and Kyle, who are our test engineers. And we have James, who is the project manager and helped Steven with the SolidWorks. And lastly, I want to let everyone know that we all worked on this project together, and a lot of these titles are interchangeable between each of us.
Just to wrap everything up, I just want to say thanks to a bunch of people. So to start out, FM Gold for sponsoring our project, and also the UMassD MNE department, and everyone here on the list. This wouldn't have been possible without everybody here, and I just want to say thanks. So thank you.
Any questions?
If your maximum temperature goal that you guys were looking for was 2,500 degrees, why select a material that was only good to 2,000?
Okay, so that maximum temperature is worst case scenario. They only have had that reach that maybe twice ever, so that was way over the top. So and if it even does reach that 2,500, it's only for like 10 minutes or a short amount of time. So that's worst case scenario. It should be able to survive within, if we have stainless steel that's up to 2,000 degrees. So.
How exactly did the light detection work? Was it reflecting off of the water, or what was going on there?
So you mean when it shines down through?
Yeah, you're saying it
How is it
shines down
collected?
through, but I'm not, like, what is
So
the actual?
So yeah, it reflects off the bottom side of the sprinkler, and then our sensor collects that. So you can see it will shine down through the water.
What is the thing that is activated?
So it collects the light. So when the plug leaves, light shines through, and then that sensor picks that light up. So that's our activation, right? When it picks up that light, it shines through.
The sensor is located adjacent to the sprinkler head, and when you saw the red light coming through and reflecting off of that sprinkler head,
Yeah.
the sensor is just to the side of that, and it's facing right at the reflection and collecting that reflection and processing that voltage into our lab view program.
And so what is present when the sprinkler is activated that is not present?
Well, there's a plug in there, so nothing comes out, like no water. And then when the sprinkler is activated, it's heated up. The plug leaves, allowing the water to come out, which also allows the light to shine through from the top down through the sprinkler head and hit that base, so it's able to be reflected back into the sensor.
Still not entirely clear on the setup, but
Maybe I can help you out. Sprinklers that you see here in the ceiling, they have a temperature ring on, it's set to activate at a certain temperature.
no, I understand, but I'm trying to get from the team like a clarity of their design.
So we have our LED up here, which
Yeah.
has a hole that connects into the pipe,
Into, so you drill it into the
Right.
pipe?
So it's inside the pipe.
Okay,
and then the light travels through the pipe, through the opening of the newly activated sprinkler, and is reflected off of this base here.
and then it's detected from the
It's
outside?
detected by this sensor right here.
Right, okay, and so did you consider, like, what did you consider in terms of the LED inside of the pipe itself in terms of design constraints?
Consider, well, we needed it to be pressure rated for water pressure. Our max water pressure is 300 PSI, I'm pretty sure, so we need a window. And then just above that window, we have our focusing lines and our LED to shine through. So as far as design, we started out with a square LED that kind of just flooded the light, whereas we found this focusing lens that kind of directed all the light down through. So
And so when you say that alignment issues or setup concerns are there, what is actually involved with the alignment and the setup?
So alignment, so the sensor that where it says adjustable holster, that sensor that circled there, we want that optimally pointed directly at the opening where the light would shine through, at the bottom of the sprinkler.
And
We want that pointed
how
there.
do you know you've accomplished that before the sprinkler is tested?
We just kind of eyeball it, even if it's off kilter, it still has collected, so it's kind of
Do
just.
you have a range on that of the tolerance of your design?
No, we don't have a range.
Any other questions?
Is, two questions, I guess. Did you look at any other design opportunities, or did you go straight to light? First
So-
off, did you guys consider any sort of water detection system, or
Water detection system. and-
like you could do like a leak detector? I have one like in my basement to know if something's flooding. So could, or
So, yeah, so to answer that, so we did go through a brainstorming phase and tried to come up with various different ways. One of the alternatives that we thought of was to put a flow sensor. So when the sprinkler activates, the flow will increase in that range. This has been an ongoing project for FM, so they've went through a bunch of different alternatives. So we were given those amount of alternatives, and we obviously eliminated those. We didn't want to go forward with those, so we tried to come up with something. And an LED hadn't been used, so.
now, was it in the scope of the project to figure out how all of these different sensors are talking to each other? You talked about how you're going to detect on one sensor that
Right.
was activated, but buildings.
So you're saying if there's like 20 sprinklers, no, so that's what's moving forward, the next part of the project that FM is going to take over. So taking one of these and putting them on, say, 20 sprinklers, and then implementing that into one simple monitor screen and data acquisition system.
Any other questions? Yes.
I had a quick question. So, what is the sensitivity of your system, of the sensor use?
Sensitivity meaning?
Is this just an on-off?
Yeah, so it's just no activation, so 0, 1. That's all.
And then how quick is the response?
How quickly, so the constraint, so the constraint we were given was plus or minus a second, and it's within that range, plus or minus a second. So.
And have you checked for any other possibility of faults around it? What are some possibilities?
Yeah, so it's the reason why it's pulsed is for false alarms. So any other light that's in the lab or a neighboring sprinkler is activated. If it's pulsed at, say this one sprinkler is pulsed at 50, the next one is pulsed at a different frequency, then there won't be any false activation from that.
So here is the question. This is partly for fire, right?
Yep.
And so the idea is there will be a fire and then the sprinkler is getting in.
Correct.
Is it possible that, like, a light from the fire before the sprinkler gets activated could do something?
Yeah, so we considered that to start, and then with our client, we went through and figured out that pulsing it will virtually eliminate any issues with that. So.
All right, any other questions? If not, please thank you.